First type, what governor, right? So this is the simplest form of centrifugal governors. Right? So this is the simplest form of centrifugal governors. You see here, this is a picture of it. It is basically a conical pendulum with links attached to a sleeve of negligible mass. Right? So this sleeve is of negligible mass. Right? The arms of the governor may be connected to the spindle in the following three ways. So here are the arms, right? As you have already seen there, these are what called as the arms, right? Okay, so these are arms, okay? And here we have the fly balls. These are links, okay? These are links, and this is a spindle. This is the stop, right? Stop for the sleeve movement, okay? And here is the bevel gear, the crank lever, and the throttle valve, right? So the arms of the governor may be connected in three ways. So this is the arm. So this can be connected either like this, or like this, or like this, right? So we'll see what is the difference between these three. The pivot P may be on the spindle axis as shown in this figure, right? So the pivot may be on this spindle axis, okay? The pivot P may be offset from the spindle axis, and the arms, when produced, intersect at O, as shown in this figure, right? So this P may be offset from the spindle axis. Either it can be here and here, like this, and when extended, it may meet at point O, right? So here it is on the spindle, but here it is not on the axis. It is offset from the axis, right? In the third way, the pivot P may be offset, but the arms cross the axis at O, right? Or the pivots may be somewhere here and here, right? This is also possible, but the cross region is O, right? So you see here, every time the intersection of the pivot with the axis is taken into account while calculating the h, right? So the distance between the ball and the intersection of axis with the pivot is what is taken for the height h, right? You see here, that is taken for the height h. But these are three ways you can connect a pivot, right? Either on the axis, or offset from the axis, or after intersection, offset from the axis, right? So these are the three ways we can connect a pivot, okay? So here are the terms, usual terms: m mass of the ball, right? M mass of the ball in kilogram, W weight of the ball in newtons, right? So W is equal to mg, small w. Then T tension in the Newton arms, right? Tension in the arms, that is in Newton. Omega angular velocity of the arm, right? So omega angular velocity about this spindle, okay? And R radius of rotation, right? So R is the radius between, so that is the length between the ball, the center of the ball, and the axis, right? So this length is the R. Radius of the path of rotation of the ball, that is horizontal distance from the center of the ball to the spindle axis in meters, right? Horizontal length between the ball and the spindle axis. Then Fc, that is centrifugal force acting on the ball in newtons, right? And we know centrifugal force is mr omega squared, right? So we'll use it, right? Mr omega squared. So here m is mass, r is this radius, omega is this angular velocity. So Fc is mr omega squared. And h, the height of the governor in meter, right? So this h is the height of the governor. It is assumed that the weight of the arms, links, and the sleeve are negligible as compared to the weight of the bolts, right? So in what governor, there's an assumption the arms, links, and the sleeve, they all are of negligible weight when compared to the bolts, right? So here is the arm, here is the link, and here's the sleeve, right? So these all are of negligible weight when compared to these bolts, right? Now the ball is in equilibrium under the action of, right? Now we are going to formulate a formula to find how much is the centrifugal force, or whatever the question is going to be asked, right? So we'll see this ball, right? We'll take any one of the ball, either this ball or this ball. We'll take this, right? We'll see this ball, if it is in equilibrium, under how many forces it is in equilibrium. If you can see here, there are three forces. 1. The tension on the arm. 2. The weight of the ball which is acting downwards. 3. The centrifugal force which is acting horizontally outwards. So, right. So based on these three forces, right, the action of these three forces, this ball is in equilibrium. Right? So now we will try to resolve this to find the answer for FC or centrifugal force. Right? How do you do that? Taking moments about point O. Right? So the easiest way is to taking moments about point O. Right? This is the point O. We can also do it by either resolving the forces horizontally, resolving the forces vertically, and to take moment about any of this, either point O or this point or this point, any of the point you can do, right? So taking moment about O is the easiest way. Why? Because one force is passing through that point O, right? So we know if we are taking a momentum about any point, any force which is passing through that point will not come into act, right? And therefore we are doing this to eliminate T, because we don't know how much is the T, right? We know radius, right? We can measure. We know mass, we can measure. Based on the angle of electricity, omega, we can even calculate FC, right? But T, we don't know. We can calculate later, right? So in order to eliminate this T, we are trying to take moment about point O, okay? So if we take moments about point O, this T will be cancelled out. So what we will be left with, we will be having FC and W. There will be only two forces, right? So taking moments about point O, we have FC into H, right? So if we take moment about O, we know that. So clockwise direction, right? Clockwise direction, we have FC into the distance between O and FC is H, right? So this distance is H, right? As you can see here, this is H. So we are taking moment about O. So I'll take clockwise direction, right? So clockwise direction, it is FC into the distance H, right? And similarly, we have another force W which is acting anti-clockwise, right? If I take moment this way, it is acting anti-clockwise. So W into distance between point O and the W, that is R, right? So this distance, that is R, right? So FC into H will be equal to W into R, right? So FC into H is equal to W into R. W we can replace by mg, right? We know which is mass into gravity, mg. FC, we can replace FC also with mr omega squared. We know centrifugal force here, FC is mr omega squared, right? So here we can put mr omega squared for FC into H, equal to, instead of W we can put mg into R, right? So when you solve it, there's an m, here's also an m will be cancelled out. So what we'll be having is r omega squared H is equal to gr, right? And this r will also be cancelled out. So omega squared H is equal to g, right? So H is equal to g upon omega squared. Okay. When g is expressed in meter per second squared and omega in radian per second, then H in meters, right? So we know g is gravitational acceleration, that is a particular value 9.81 meter per second squared, right? H we have to find. Omega, it is angular velocity, right? So omega can be replaced as 2 pi n by 60, right? So we know we can write omega as 2 pi n by 60. Okay. Here 2 is a numerical value. Pi is a numerical value, 3.14, something like that. 60 is again a numerical value, right? So only term is n, right? So when you replace this omega with 2 pi n by 60 here in this equation, what we'll be having is H is equal to, if I replace g with 9.81, okay, H is equal to 9.81 upon, right, 9.81 upon 2 pi n by 60 whole thing squared, right? Omega squared, that is 2 pi n by 60 whole thing squared, right? So when you solve it, you'll be getting H is equal to 895 upon n squared meters, right? H is equal to 895 upon n squared meters. Here they have taken g as 9.81. right? So as you can see, the edge, the height is solely depend on the speed, right? We see from the above expression that the height of the governor edge is inversely proportional to n squared, right? So when you see here, the edge is inversely proportional to n squared, which means if h increases, n squared decreases. If n squared increases, h will decrease, right? So we can feel it here, right? If n squared increases, if n squared increase means speed increase. If the speed increase, the balls will move this way, right? So if the balls move this way, the h will decrease, right? On the other hand, if the n squared decrease, which means the speed decreases. If the speed decreases, the balls will go this way up or down, right? So in that case, the h will increase, right? So that's why it said h and n squared are inversely proportional. Okay. Therefore, at height, the value of h is small, right? H is inversely proportional to n squared, and therefore, at high speeds, the value of h is small. Why small? Because it is in n squared. Here only h, right? So say for example, if you put 10 here, your equation will show it as 100, right? Why is that? It is squared. And that's why therefore at high speeds, the value of h is small. At such speeds, the change in the value of h corresponding to small change in speed is insufficient to enable the governor of this type to operate the mechanism to give the necessary change to the fuel supply, right? So such type of governors, if the change in the n at high speed is small, so small, right? That is not enough to give the governor direction to open or close the throttle valve. Say for example, at 100 RPM, right? Say for example, if n is 100, then n squared is how much? 10,000, right? So 895 upon 10,000, we will have some value for h. Right? At 101, right? Then we will have a huge number here. So the change would be so small here in h, right? So this change in h, right? The small change in h is not enough to activate whatever the mechanism here, right? Give the necessary changes to the fuel supply, and therefore this governor may only work satisfactorily at relatively low speeds from 60 to 80 rpm, right? So the satisfactory work limit for this type of governor, what governor is 60 to 80 rpm, right? 60 to 80 rpm. So this is not hard and fast rule, but usually the efficient working range is given as this range 60 to 80 rpm, right? So here is a numerical on what governor, right? A simple question. Calculate the vertical height of a watt governor when it rotates at 60 rpm. Also find the change in vertical height when its speed increases to 61 rpm, right? So we now have to find what would be the height of the watt governor for 60 rpm and 61 rpm, and then we have to find the difference between the height, right? So we'll apply it in the equation, right? So equation says h is equal to 895 upon n squared, right? So accordingly, N1 is given 60 rpm, N2 is 61 rpm, right? So we know that initial height H1 is equal to 895 upon N1 squared. Right? So N1 is 60, so 895 upon N1 squared, which is 0.248 meter. Okay, and this is for the speed at 60 rpm. Now we are going to find for 61 rpm. So similarly, H2 is 895 upon N2 squared. So 895 upon 61 all things squared. So that is 0.24 meter, right? So now the question is to find the change, right? The change in the vertical height. So how to find the change? So we have first velocity, first height. We have the second height. We just have to find the difference between these two, right? So change in the vertical height, h1 minus h2, that is 0.248 meter minus 0.24 meter, that is 0.008 meter, that is 8 millimeter, right? So there you can see h1, the height, that is 0.248 meter at 60 rpm. When the speed is low, the height is high. when the speed is high, the height is low, right? So it is inversely proportional, right? So there you can see the change in the vertical height is 8 millimeter, right?